Okay, in this short little tutorial, I want to show you the PhET simulator and how to make an electric circuit. I want to point out how to introduce meters and some subtleties about voltage that didn't necessarily come out through the tutorials. And then I want to talk a little bit of what I want you to do for a lab that I'll post on Schoology in a bit. So we're just going to build a simple circuit, and then we're going to use some meters here, something that you would have to do in lab, because if you want to talk about current or voltage, you have to measure those. And then from those two measurements, and eventually a third measurement we'll learn about, you can determine power or energy, right? Remember, power is the product of voltage and current, and energy is the product of power and time. So energy is essentially voltage times current times time. Okay, so let's start with our voltage source, a simple battery. Right? So when I put there, I've got potential across here and here. In fact, let's introduce our first meter, a voltmeter. So when you want to measure a difference in potential, okay, you have two leads. You place one lead wherever you want. I'm going to put it at the positive end, and I'm going to put the other one at the same spot. We put it there. I see 0 volts. Well, this is a 9-volt battery. Okay, if I click it, yep, sure enough, it reads 9 volts. So why is that reading 0 volts? Because when you measure voltage with a meter, you're measuring, again, the difference between two places. Since these two places are both at 9 volts, there's no potential difference there, so nothing happens. If, on the other hand, I move it here, I see that it's 9 volts. So there's a 9-volt potential between those two. Now, this might seem obvious or silly, but it's actually very, very important when circuits become a little bit more complex. It's a simple concept, but it can get confusing when things get complex. All right, and I could certainly move it here, and we'd expect 0. Now, technically speaking, you got to make sure you understand the difference between potential difference and just potential. The potential at this spot is 9 volts. The potential at this spot is 0 volts. The difference between two is 9 volts. The difference between two spots on the positive side is 0. So that can, again, be a little bit confusing. All right, so let's make a, I'm going to put this back, a circuit with, so we're going to use our load as a resistor, okay? Just some generic resistor. And then I'm just going to try to make a square circuit. Actually, before I do that, I want to introduce our second meter. The second thing we want to measure in any circuit is current. And so you measure current with what's called an ammeter, A-M-M-E-T-E-R. There's no amp meter. And this simulator has two. One is a cheat, which is not realistic for what we would have in a lab, so I'm going to avoid that. The other one is an actual one where you have to put it in the circuit. Okay, so an ammeter has to be connected in a circuit differently than a voltmeter. And a voltmeter, if I bring that out, I could just touch the two leads anywhere I wanted to and measure difference. An ammeter, you can't do that. An ammeter has to be part of the circuit. It doesn't matter where you put it. So before I make all the connections, I want to put my ammeter somewhere. I can put it here. I can rotate it here. As long as it's part, it doesn't matter where it goes. So I'm just going to leave it right here. Okay. So since nothing is going on, even though there's a voltage source, there's no connection, I've got no current. So let's say I were to do this. Okay, so I'm going to connect this to here with a wire. What do we expect the current to be? Okay, so I've got this is already on. There's no switch. All right, make a prediction. Notice that the load is not connected, and I connect it. I got nothing. Okay, there's no reason for charge to flow for the simple reason there's no completed circuit. Remember, the rule of any circuit is the positive and negative have to be connected in some sort of loop. Well, I've got a broken loop here, so nothing's going to happen until I make those complete connections. Same as I do here. All right, so I'll just finish this, and we should be good. All right, so I've got 0.98 or 0.90 amperes in here. And we see the current flowing. So I want to point out another important thing to build off what I was talking about voltage before. So I'm going to take this lead and put it right there. And I'm going to put the lead here. And we know this is 0 volts difference, even though both points are at 9 volts. So the question is, what effect do the wires have? Well, if I want to measure the difference between the red and here, right there, I get 0 volts. What that's telling me is I already know the red is at 9 volts. Well, then this part of the wire must also be 9 volts. So the difference between these 2 points is 0. And then what's important about that is no energy is being used. There's no joules given up for every coulomb that moves through. So the wires these are ideal wires. They're just acting as conduits. And if I move the black lead here, still 0 volts. Now, is there going to be some difference when I get through the ammeter? Nothing. Nothing. So from here to here, right, they're all at 9 volts. So think of a river where it's at the same altitude. Every part of here is at the same altitude, and it's a high altitude because it's a high potential. So what happens when I go on the other side of the load? Well, remember, what is the point of the load? Actually, I'm going to use conventional current because that might make it a little easier. So the charges are moving this way, even though technically the positives aren't moving. That's conventional current. Okay, all the charges here have high potential. What's the point of the load? To use up the energy, so we expect the potential to drop across that load, like water going over a waterfall, and sure enough, I see 9 volts. So this is at 9 volts, the black is at 0 volts, so the difference between these 2 points is 9 volt drop. And as I move the lead here and here, the say 9 because we're right back to the negative side, and the negative side, remember, is at 0. So this is 9, so the difference is 9. So the really important point to look at this is everything in the circuit before the load, in an ideal situation, is at the high potential. And then when you go on the other side of the load, you're automatically dropped to 0 until you get back to the negative side. So the wire is just an extension of the negative part of the battery. Okay. Now, let's talk about current. It's 0.9 amps here. What if I'm going to use my cheat one, because it would be a pain to try to move this into this part of the circuit, because I'd have to break the circuit apart and reinsert it, etc. So this is a cheat that gives me the current at any point. I don't know if there's a real-life analogy to this. If it is, it's fairly high-tech. So we expect 9 amps there. And as I move it across here, a very important point that you want to understand is the current is the same everywhere here. Okay, because remember, what is current? It's a measure of the charge flow, and the charge flow is the same everywhere in a circuit. Doesn't matter whether it's at high potential or low potential, it is the same. Okay, and that's really just a law of conservation of charge. The voltage rule I told you is really just a law of conservation of energy. All right, now, what happens if we have real wires? Okay, in real wires, we call something wire resistivity. The wires have actual resistance. So I'm going to give them a fairly small resistance. And I want to show you something that's pretty important and something I'm going to try to explore with the lab, just to make it a little more interesting. So if I put the leads at the same spot, I see there's 0 potential difference as we expected. And I'm going to put it now in this corner. Now all of a sudden I see that there is a potential difference, a very small one, between this point, which remember is at 9 volts, and the difference is 0.29, so this must be at a potential of about 8.7. Okay, 8.79, the difference is 0.29. So why is there all of a sudden a difference between these 2 points of potential? If there's a drop in potential, there's some energy be given up. So why is that? What's changed? Well, clearly we put resistance in the wire. So a really, 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 really important idea is resistance in a circuit converts electrical energy into other forms. In fact, the form you'd expect here would just be thermal energy. The wire gets warm. And if I move the lead over to here, so I'm going across more wire, there's even a bigger drop. Okay, so the more wire you're using, the more drop in potential, the more energy is given up to the wire itself. You want to avoid that. So that's why we talk about ideal wires initially. Now let's see what happens when we go across the ammeter. If I go to the other, let's here, this is 0.78. If I go to the ammeter, 0.78. So what can we infer about the ammeter itself? If there's no difference in potential between the right side and the left side, that tells us that there's no drop in potential, therefore no energy is being used up. Why is there no energy being used up? Oh, the ammeter, an ideal ammeter, has 0 resistance. Okay, and then we go here. It seems to be a gradual drop. Now, we're going to go to the other side of the resistor. What do we expect about the drop across resistor from the previous idealized version? Well, if you recall, that was like going over the waterfall, so we should expect to see a big drop. And sure enough, there's a big difference now. This is at 9. This must be at around 0.7 because we've dropped a full 8.23. Some of that because of the wire, most of it because of the resistor. So you can infer something about the resistance of this guy compared to the resistance of the wire based on the fact that we had a huge drop here. So it's contrast. All right. So there is a 1.05 difference here due to the wire drops. And then when we go to here, there is an 8 drop. So we have a huge drop because of the resistor. And what makes the resistor difference? It's resistance. It's large compared to the wires, as you want. And then as I go more and more wire, eventually I get to the 9 volts. Now, this assumes something about the battery itself, okay, and that there is no resistance in the battery. We're going to treat our voltage sources as ideal, and ideal means it has no resistance. We'll eventually come back to investigate what happens when it does have resistance. All right, so the last thing I want to talk about is what we're going to do for a lab, and I'll lay it out on a sheet and post it on Schoology, is we want to look at what is the relationship between voltage drop and current in a circuit. And you're going to do it for 2 different parts of the circuit. I want you to do it for 2 points from the positive part of the battery to some point along the wire. Okay, either this corner or this corner. Choose a corner. So I'm going to choose it right. Actually, I'm going to change mine. We're going to do it here and just before we get to the load. All right, so what you're going to do is measure the voltage drop, the current. That's easy to do. And then you're going to do it again just simply by moving it here and measuring the voltage drop on the other side of the load. Okay, I'm not going to worry about moving it to a 3rd spot. And notice that the current doesn't change. The current doesn't depend on the meter where I move this thing. The current is staying the same no matter where I put the meter. It shouldn't change. We wouldn't expect it to. The meter shouldn't affect what we're measuring. Okay, so once you've done that, that's one set of data, right? We've measured 2 voltage drops and 2 currents, which happen to be the same. I'm going to ask you to calculate the power through each one. You've got an equation for that, so we don't have a meter that measures that directly. And then what I want you to do is to change the voltage in the battery. You do that's pretty simple. You just click on the battery, and it's at 9 volts now. You choose some arbitrary one. You can go up by small increments, large increments. They don't have to be equal increments, but I'm asking you to do about 5 or so different voltages. And then go back to here, measure, measure, and then you're going to make a simple graph from that. Okay.